Okay, let's take a look at the rules for drawing Bode plots. And these all come from the laws of logarithms, the properties of logarithms, and also limits as frequency gets close to infinity or close to zero, and some of the things that happen. And you can make some approximations with those limits, and then you can use the properties of logs to make some simplifications. And so the first thing to be aware of is for power, the gain in decibels is 10 times the log of the gain. But for voltage, and most of what we're looking at is voltage, is that our gain is going to be 20 times the log of the voltage. And usually that's what we're looking at. And so right here, I was trying to grab a print screen, but I can't. Okay, so the gain in decibels is going to be 20 times the log of the magnitude of the transfer function. Let's see, did that? Oh, it did kind of copy over nicely. All right. So ultimately, that's where this is all coming from. And if you go back and look in the book or look in your notes and go over it, you can see where all of these things come from, and it's not so much of a mystery. However, if you're not you don't really enjoy looking at the math, you can just learn what these rules are. Okay, so you'll have a transfer function, and the transfer function is going to look something along the line. You'll have a constant, which we denote with capital K, and then everything else, you may or may not have any of these. So in the numerator, you might have some zeros, and that would be j omega to the capital N, so that's just, the N is just the exponent. Those would be zeros at the origin, and you might have some simple zeros that you would write like that. And you might have poles at the origin, and they would be in the denominator. Or you might have simple poles, and you might also have quadratic zeros. So that's J2 C omega over omega C. That's an omega C, corner frequency, plus J omega over omega C squared to the n power. So you could have a quadratic zero, and you could also have a quadratic pole. And each one of those factors will contribute to the magnitude of the gain, or to the Bode plot in a particular way. And I think I will go ahead and just write those down here so that you've got them. I won't do this chart, because this chart, I think you have it in your book. If you need a copy of it, you can just email me and I'll get it to you. So this one, I think, is pretty clear, and you can just refer to it. But to get the magnitude, it might be useful to have the following rules handy. So when you're trying to find the magnitude, then you would take for the constant term, you're going to add all of these up. So the sum of all of these. So you would have 20 times the log of the magnitude of the constant. It's for the constant term. And then for a 0 at the origin, it would be 20 n log omega, and for a simple 0, it would be 20 n log omega. Actually, it's better. A better way to do it is like this. To do it as 10 n log 1 plus omega over omega c squared. It is equivalent, and this is better because there's no j in it, because you already got the magnitude part taken care of. Okay, so there's a simple 0, and then pole at origin. You would have minus 20 n log omega, and for a simple pole, you would have minus 10 n log 1 plus omega over omega c squared. And then you have the quadratics, and for the quadratics you would get quadratics. They're messy. It's easier to think about what they are like in the limit. If we have to do one of those, we'll write down the formulas for the quadratics, but they're just kind of messy. Alright, and I'm not planning to do one today. So let's take a look at an example. Let's say that we had transfer functions is a voltage transfer function of so we've got a 0 at the origin on top, and we have a simple pole on bottom. Now we have to get this in the correct form. We need the bottom factor to be 1 plus something, so we need to factor a 10 out of the bottom, and we'll put the 100 in front because then we can see it as part of the constant. Okay, and then so this then becomes alright, so now we have a constant factor of 10. We have a 0 at the origin, and it's degree 1. And we have a simple pole with omega c equal to 10 radians per second. Okay, so now let's do the Bode plot first. Okay, so for the constant factor, we need to take 20. So for the constant factor, take 20, and that 20 is just because of the definition of the voltage gain. 20 log 10. Well, the log of 10 is just 10. So this gives us 20. So that's a constant term, constant 20. And so we can put that in as a horizontal line at 20. All right. So that is our constant term. Now for our 0 at the origin. Zeros at the origin have a line that goes through 1 and has a slope of 20 n decibels per decade, where n is the exponent or the order. And so ours did not have an exponent, so its n is equal to 1. So it goes through 1 and has a slope of 20 decibels per decade. So what that means is goes through 1. See, that's 1 right here, because I always mess this up and get my axis in the wrong place, so I'm going to make sure that I have my axis well defined. That's just so I can see where my I can see where my axis is. Okay, so there's my axis, and I need this to go through 1, which is right here, and has a slope of 20 decibels per decade. So that a decade is from 1 to 10, or from 10 to 100, from 100 to 1,000. So there to there. There to there. Okay, so this one is 20 log omega. see, how would I write this? I would 0 at origin. And then that one is 20 log omega. And my constant is 20 log 10. Okay, and then this was 0 at origin. Okay, now we have a simple pole, and for the simple pole, we will have simple pole will go through omega c and have a slope of negative 20 n decibels per decade. N here is just 1 because it has no exponent. So we'll go to omega c. So omega c was 10. So we'll go to 10. Let's see. That's 1. So here's 10. And a slope of negative 20 decibels per decade. This semi-log paper is not exactly perfect. And then up to where it hits the axis, up to that point, it is 0. Okay, and then our final plot is going to be all of these added together. So when we think about adding these together, let's look at the segments. So from 0.1 to 10, I have a line at 0 that's not going to do anything. I have a line at 20, that's a constant, that's a constant of 20. So what that will do is it'll take this other line that I have left and shift it up by 20. Or you can think of it as, let's add together these 3 points, negative 20, 0, and 20, add those together and you get 0, and then go to the other end of the straight line and add those points together. That would be 0 plus 20 plus 20, which is 40, and you get that line. And then we can put those together. Let me do this in a different color because it is our answer. So this is our Bode plot right there. Notice all it is, the 0 part you can ignore. You take the line and then shift it up by 20 because you have that constant 20 there. Okay, now you want to think about what's happening beyond here. So beyond this point, we have the same 3 that we had before. Well, really just 2. We still have this red line, we have this green line, but now we've added a line that has a slope of minus 20. So you can add slopes together to see what your slope is going to do. So here I have a slope of plus 20, and then I have a slope of plus 20, and now I add a slope of minus 20. Plus 20 minus 20, the slopes will cancel out. So this one had an upward slope of 20. Now I'm adding a downward slope of 20. That'll just make it go horizontal. And so that's what our Bode plot looks like. And then if I wanted to get the magnitude of the gain, then I would take 20 log 10 plus, and then for a 0 at the origin, oh, I need to know what the frequency was. So let's say the frequency was, let's say omega was 300. So omega is 300. So it'd be 20 log 10 plus, where did I put those notes? Log 10 plus, so we had the 0 at the origin, and then we have a simple pole, so that's minus 10 log oh, 20 log 300. This is the 0 at the origin. And then the simple pole will be minus 10 log one plus my frequency 300 over my corner frequency, which was 10 squared. And then I would evaluate that and figure out what it is. And I will do an example of that in the next problem. I just don't feel like getting out the calculator. Okay, so let's do another one. Let's say I had h, my transfer function, equals 0.01, 1 plus, actually, let's do 5 plus j omega over 10 j omega times 200 plus j omega. Okay, now let's get this into standard form. So I've got my 0.101. I'll factor a 5 out, and I have 1 plus j omega over 5. Then I have 10 j omega, and then I'll factor 200 out of that, and then I have 1 plus j omega over 200. So now let's see what my constant term is. So my constant term is 0.01 times 5 over 10 times 200. And then I have 1 plus j omega over 5. So this is a simple 0 with corner frequency equal to 5. And then I have j omega, so that is a pole at the origin. And then I have 1 plus j omega over 200, so that is a simple pole with corner frequency equal to 200. And then this number is 0.00025. Do y'all mind terribly if I change the problem at this point? So I'm gonna make this, instead of 0.01, I'm gonna make that 100. And this gets me 0.25. Just a nicer number. So now I have my function in standard form, my transfer function, h of omega equals 0.25, 1 plus j omega over 5, and then j omega 1 plus j omega over 200. And let's say I want to determine, I also want to determine, in addition to a Bode plot, so do a Bode plot, and determine the exact total response in decibels. When omega equals, let's say 500. Okay, so now we want to first do our Bode plot. Okay, so we'll get our constant for our constant term. A constant term is 20 log k. And that gets me negative 12. So from my constant term, I will have a line at about negative 12. So if that's negative 20, negative 10, so I'll say negative 12 right there. Alright, now I'm going to put a line through my axis because I always mess that up. Alright, now I have a simple zero corner frequency equal to 5. Simple zero corner frequency equal to 5. So simple zero, it will start at omega c and then have a slope of 20 n decibels per decade. So omega c is 5. So right here is 1, right here is 10, so 2, 3, 4, 5, so here's 5, and up till 5 it is 0, and then after that it is 20 decibels per decade. So I'll go to 2, 3, 4, 5 right here. And that would be this line. So this is 1 plus j omega over 5. Alright, and then we have our pole through the origin. And we had one of those in our last problem. That goes through 1 with a slope of minus 20 decibels per decade. I'm about to make a mistake right here in the recording. When I draw this pole through the origin, I'm going to draw it that it goes at 0 up until 1 and then it slopes down, but really it should continue and it goes through 20 on the gain axis here. And I do go back and fix that later, but I just want to alert you that I'm about to make a mistake and draw this line. I'm about to put it right there where it doesn't belong, so just heads up on that. So that's 1 over j omega. And when, well, we'll do that in a minute, okay? And then we also have a simple pole, and a simple pole starts at omega c and has a slope of minus 20 n decibels per decade. So omega c, so simple pole, omega c equals 200. So here is 100, so here is 200, and has a slope of minus 20 decibels per decade. So okay, so now to add all this together. So up till here, this first part. So we're going to divide this into regions. And you can look at what the slopes are doing to each other. So we start with our constant value, and that's just minus 12. And that's it, and up to that everything else is 0. So we'll be right here. And then we add a slope of negative 20. And we have that slope of negative 20 until we get to this point, which I believe was 5. So it's going to be parallel to this line. Okay, and then when I get to this point, I'm adding a slope of positive 20. And so that's going to level out. So my negative 20 slope plus my positive 20 slope will level out, and I will have a horizontal line until I get to the next point. And then here, I'm now adding a slope of negative 20, so I'm going to have a slope of negative 20 again. And that would be what my Bode plot looks like. Shoot, I just realized I messed up my my simple 0. My simple 0 should have looked like, it did not, should have looked like this. It did not, it was not 0 before that, so that means that this part of my answer is not right. I forgot that the simple zeros are not zero. The simple zeros are not zero before 1. And so the Bode plot from 0 to 1 will be this slope of minus 20, but shifted down by 12. So you'll go down 12, so this is 20 minus 12, so that'd be at about 8. And then it connects there. Try one more time. There we go. Okay. All right, that's better. Okay, so that's correct there. Okay, so now let's get what the exact total response is at omega equals, what did I say? Omega equals 500. So at omega equals 500, where's my graph? Okay, so at omega equals 500, we will have minus, well, we'd have 20, the 20 log k, well, we already know what that is, that's minus 12, plus, and then we have our simple 0, which will be 10 log 1 plus 500 over 5 squared. And then we have our simple pole, that'll be minus 20 log 500. And then we have, so that was our pole through the origin. And then we have our simple pole, and that'll be minus 10 log 1 plus 500 over 200 squared. Okay, so let me just do that a little bit neater underneath this. So for our constant term, that was minus 20 log k, and that got us negative 12. For our simple 0, you'll have 10 log 1 plus omega over omega c squared. So that got us plus 10 log 1 plus 500, which was given in the problem, over 5 squared. Then we had our pole through the origin, and the pole through the origin is just going to be minus 20 log omega, so this will be minus 20 log 500. And then for a simple pole, if we had a 0 through the origin, it'd be plus 20 log omega. A simple pole is 10 minus 10 log 1 plus omega over omega c squared. So that's minus 10 log 1 plus 500 over 200 squared. This is minus 12 plus 10 log 1 plus, well, I'm going to do this whole thing. I'm actually not going to do it because I would only make a mistake. But you would do all that on the calculator and get a number from it. And then that would be the exact value of your magnitude.